So my name is Peter, and this is work that I've done with my advisor, Lisa Wexler, and also Charlie Conroy here at Santa Cruz. And this is really a work trying to confront observations with simulations of dark matter to say what can one inform the other, and then how can we all make them self-consistent and derive new information out of that. So the idea is to connect dark matter halos to galaxies throughout cosmic time. And we know that in the real universe, there must be some relationship between dark matter halos and stellar mass in galaxies, just because, well, you know, the real universe, we presume, obeys lambda CDM. On the other hand, we don't really know what this relationship is at very high redshifts. We have good constraints at redshift 0, how stellar mass fits into halos. However, at redshift 8, we have no idea what it is. So the approach we take is to parameterize what the stellar mass to halo mass relationship can be as a function of time. And we take the functional form at redshift 0 and add in several different parameters to model very flexibly about how it can evolve to redshift 8. And then we ask, well, what happens when we pick a particular point in parameter space for the stellar mass to halo mass relationship? And so given a dark matter simulation and a particular choice of this relationship, we can place galaxies into halos at every snapshot of the simulation, starting from the very beginning and then stepping forward in time. And as you do this, you can see very clearly that you can create galaxy growth histories, meaning that you see how much stellar mass there is in a halo at one redshift. At the next redshift, you say, oh, it got a little bit bigger. So we can infer then what's the star formation rate of this galaxy, or rather this halo now, given a stellar mass to halo mass relationship. So if we know stellar masses in all halos, and we can infer star formation rates, then we can start calculating observables. So we can derive the inferred stellar mass functions, which is just counting up all the halos with a certain stellar mass, or the cosmic star formation rate as a function of time, or specific star formation rates, looking at the star formation rates inferred as a function of stellar mass. And then we have a whole bunch of nuisance parameters to model all kinds of observational errors and biases, offsets, for instance, in calculating stellar masses or star formation rates as a function of redshift. And then we go ahead and compare with data. So our initial guess for the stellar mass to halo mass relationship is now confronted with observational data, and we can calculate a likelihood for that. And so then once we know the likelihood, we can repeat in an MCMC method to derive the parameter space, which is allowed by both the simulations and the observations, for how galaxy stellar mass maps to halo mass throughout the very beginning of the universe to the time which we are present today. So that's the basic approach. Let me tell you now a little bit about the data sets which we use. The simulation data is from the Bolshoi simulation run by Anatoly here. And so as part of this, we have new calibrations of halo mass functions, satellite fractions, and merger rates, all the way from redshift 0 to redshift 8 from the Bolshoi simulation. And on the observational side, we have data sets. We're using new stellar mass functions from Primus, from redshift 0 to redshift 1. We're the first paper actually to use these for theoretical purposes anyway. And we also have a new compilation of cosmic star formation rates all the way to redshift 8. And as a few of the redshift, I guess, high redshift people were talking about earlier today, there's been changes in what we estimate for the cosmic star formation rates above redshift 2. And so this is old news to many of you, but actually now we can very well match the buildup of stellar mass and the cosmic star formation rate in the universe. And as a matter of fact, what's being shown here, these data points are from the new compilation of data. The red line is our best fit model, and the red band is the posterior distribution. And on the left-hand side, I'm showing you stellar mass functions all the way from redshift 8 to redshift 0. The redshift 8 ones are derived by using the Gonzalez et al. Conversion between luminosity and stellar mass. But we've checked to make sure our results are robust to excluding all redshift 7 and 8 data. But the point is, our best fit model lines go through all the data points for stellar masses which people have reported. And of course, also the same is true for specific star formation rates. We also made a new collection of specific star formation rates all the way to high redshifts. And actually, it's very encouraging to see that now at 10 to the 9.5, solar masses, it's not quite so flat, and actually the data points are more in agreement with where our line would go through them. Okay. So what are the main results? What can we learn from doing this analysis? So the most obvious thing is simply write out of our parameterization. How does stellar mass map to halo mass as a function of time all the way back to redshift 8? And this is very important for calibrating both semi-analytic models as well as simulations. And obviously the error bars get more and more, get larger as you go back to higher and higher redshifts. But it's still very interesting to know that today, at least for Milky Way galaxies or Milky Way size halos, they've reached essentially the most efficient integrated star formation as a function of halo mass over all time. Other more interesting things, I said we can derive star formation rates. So here's a very clear picture then of all the star formation which has ever happened that we've observed anyway, as a function of halo mass and redshift. And you can see a very clear peak towards earlier and earlier times. We don't have any halos that are this massive at this early times, but you can see if we did, probably they'd have higher and higher star formation rates as well. And as of course, as you go to lower and lower times, I guess lower redshifts, later times, then you get less and less star formation as the accretion rates have been decreasing over this time. And these white lines show you the trajectories that individual halos would take, or on average, an ensemble of halos would take. And so a 10 to 15 solar mass halo would sort of cut through and hit the brightest point at around redshift 2 to 3-ish. And here now I've sort of unbent the trajectories. And so now this is showing you for the halo mass today on the y-axis as a function of redshift, what was the star formation rate in individual halos. And so you can see very clearly that massive halos have peaked in their star formation around redshift 2 to 3, and less massive halos have actually sort of increased in their star formation from very early times to the present day. And actually, if you look at where this peak happens, for very massive objects that happen between redshift 2 and 3, but as you get to lower and lower masses, it's sort of, you can see clearly that the peak is shifting towards later and later times. And so why is this? We can look at the star formation rate divided by the baryon accretion rate and see what that tells us. And in fact, the baryon accretion rate, we can't tell from dark matter simulations, but we can estimate it by the dark matter halo accretion rate times the cosmic baryon fraction. And what we can see from this is immediately that 10 to the 12 solar mass halos have had the most efficient rate of conversion of incoming matter to stars ever since we have observations to check this. And so this rate has remained almost, I mean, very constant between 20 and 40% of incoming baryons turned into stars ever since redshift 8. And all other masses of halos have had lower conversion efficiencies, and especially so for the most massive objects, which we can clearly see, and probably so for dwarfs as well, although we don't have observations to constrain them to higher redshifts than just the local universe. And so this is for a fixed mass. So if I took a Milky Way size halo at redshift 2 or redshift 5 or redshift 6, the efficiency would look like this. And this is now for following trajectories of halos. So if I have in the red line now a Milky Way size halo today, what was its efficiency as you go back in time? And so you can very clearly see the imprint that this sort of maximal efficiency has. Because all the halos, when they reach that, when they accrete enough matter to reach that sort of golden mass, then they're very efficient at turning incoming baryons into stars. And once they accrete beyond that mass, then you can very clearly see a decline to the present day. And so this sort of imprint is responsible for this rising and falling in the star formation histories. And so the star formation histories that I showed you here were average. So for an ensemble average of halos of mass 10 to the 14 solar masses, for instance, they would follow the green line. But we can also place constraints on individual star formation histories, just from looking at individual halo mass accretion histories and applying our stellar mass to halo mass relationship with some scatter. And so these are now constraints on individual star formation histories as a function of halo mass today, so 10 to 11, 10 to the 13, 10 to the 12, 10 to the 14 on the two sides. And I guess something which many people have wanted to know is what's the formula which best matches? And so usually the formula which people have used is a declining exponential. And as you can see, this is definitely not a declining exponential. It looks very different. And especially at high redshifts, you should never be using a declining exponential because, in fact, it's a rising power law. And if you wanted to use a more complicated star formation history to describe more recent times as well, you could use a rising power law multiplied by a declining exponential. Or if you really wanted to be fancy and had very good spectroscopic data, it might make more sense to have a broken power law. In other words, one rising and then one falling power law. And you can see the quality of the different fits. Yes. Yes. So the mass is 10 to the 12 solar masses today. So if you were fitting its SCD today, you'd want to know what its star formation history was at all times. And this tells you. Yes, so now a little bit, thank you, a little bit about the other kinds of interesting constraints which we can get. So one of the nuisance parameters which we model is incompleteness. And that is, at high redshifts, you might expect some incompleteness because you're detecting galaxies using the Lyman break technique. And so if you have some galaxies which aren't star forming, you'd expect maybe they don't show up in your Lyman break survey because there's no break to separate, I mean, the UV from not, because there's not enough star formation. But if we check for this, we have parameters to control for this kind of incompleteness. And as a matter of fact, we find that it's not necessary to include a lot of incompleteness in early redshifts. And let me just explain where this constraint is coming from. Because we know the stellar mass density at very early redshifts and we know the star formation rates, we can ask, is that consistent with how much stellar mass and star formation rates you have at later times? So if you're missing a lot of stuff at early redshifts, then you expect to see that actually at later times you have this unexplained increase in the stellar mass density, which is not accounted for by the star formation rates. And that's not actually what we see. We see actually everything seems to be fairly consistent without the need for a lot of incompleteness at high redshifts. Something else which is very interesting that we can constrain is how much star formation comes from inside the galaxy, in situ star formation, versus from mergers. And let me explain the reason why we can constrain this. So the stellar mass function, growing as a function of time, the stellar mass function tells us the stellar mass growth of galaxies as a function of time. The star formation rates tells us the in situ star formation. And so if those are different, then what that means is that more stars are coming in from mergers than you just have star formation. And so by subtracting the total stellar mass growth from the in situ star formation, which comes from the star formation rates, we can derive then the fraction of growth which comes from mergers and the fraction of growth which comes from in situ star formation. And so this shows you, on the axis is the fraction of stellar growth from in situ star formation. And of course, for lower and lower mass galaxies and halos, you have more and more, a larger fraction coming from in situ star formation, simply because the relationship between stellar mass and halo mass, the slope is very steep as you go towards lower and lower mass halos. And so if you think about the merger spectrum being largely the same, I mean with some modifications, a 1 to 10 merger in dark matter halo mass actually can mean a 1 to 30 or 1 to 100 merger in terms of the galaxy mass as you go towards very low halo and galaxy masses. And so as you go to higher galaxy and halo masses, on the other hand, and higher redshifts, well, so as you go higher and higher here at low redshifts, actually most of the growth is coming from mergers. But as you go to higher and higher redshifts, then actually less and less is coming in from mergers. So let me just finish with a handful of slides about when and where all the stars were formed, because we can now put constraints on this. And so what I'm showing you here is a function of halo mass in time since the Big Bang, just a map of the star formation rate as a function of halo mass times the number density of halos. So this is a heat map to show you where all the stars in the universe were formed, and these contours, the thick one shows 50% of all the stars in the universe. The thin one shows 90% of all the stars in the universe. And that dashed line shows you the median halo mass above which 50% of the stars were formed at any given redshift. And actually, the surprising thing which you see here is at any redshift, essentially 50% of the stars were formed above the Milky Way's mass and 50% of the stars were below, except at the very highest redshifts, where in fact we just don't have enough halos of that mass. The exponential decline of the halo mass function cuts off any star formation in such halos. And here's the same plot, now just in the vertical axis instead of halo mass, I've shown you stellar mass. And again, with the same contours, the same meaning, the dashed line is the median galaxy mass in which stars were formed. And of course, thick contour is 50%, thin one is 90%. What I can add in this one is a dotted line showing you the limit of current observations. So it's a function of redshift, what's sort of the faintest galaxies which we've been able to observe. And I can then go ahead and integrate and tell you that we've actually observed the stellar mass ranges in which 90% of all the stars in the universe were formed. So this is encouraging, a little bit depressing, because it means we've seen most of the action. But of course, there's also a lot of interesting physics that's going on down here that we want to learn about. So I just thought that would be a nice thing to close with and give you a little summary. Most of the stars in the universe were formed in halos similar in size to the Milky Way, and of course also galaxies similar in size to the Milky Way. And the reason for this is, of course, this is where the conversion efficiency peaks. So 20 to 40% of the incoming baryons getting turned into stars right around this galaxy and halo mass. What's somewhat more surprising is this efficiency has remained relatively constant over time. So in terms of the histories, galaxies and more massive halos initially formed stars efficiently, but then their star formation rates dropped. And that's just because their halos were going through this special 10 to the 12 solar mass maximum efficiency. And galaxies in less massive halos, well, you can say that because they haven't yet reached the maximum efficiency, they have increasing star formation rates which sort of flatten out at late times as their overall accretion also flattens out. Excuse me. High redshift star formation histories are well approximated by power laws, as we saw. And high redshift incompleteness may not be so worrying after all. Of course, we'll need deeper observations to confirm this prediction. And finally, at high redshifts, most galaxies build up most of their stars through internal star formation, although at very low redshifts, I mean, essentially from redshift 0 to redshift 1. I know I shouldn't be saying very low for redshift 1 anymore, but at late times, these massive galaxies build up most of their stellar mass through mergers. However, I should add, I didn't show you the slide, but it's everything I've said here is in the paper, which you can find the archive number on the upper right-hand corner. In fact, for these galaxies, a lot of stellar mass is incoming in mergers, so much such that not all of it can fit in the central galaxy. And so you find that, say, above 10 to the 14 solar mass halos, something like less than 10 to 20% of all the stuff that's coming in from mergers, all the stars that are coming in from mergers, can make it into the brightest central galaxy, and all the rest has to go into the ICL. Okay. So thank you for listening, and are there any questions?
Pascal.
Yeah, I'm just a little confused. You were making this comment before about the merger being much higher.
Yes.
But yet your plot shows essentially everything is formed from each of the bottom redshift. So I'm just wondering, how does this fit together?
Right. The way it fits together is that the star formation rate is increasing so rapidly that after you have a merger, I mean, at very high redshifts, the halos are small. So after you have a merger, then your mass increases, and you're probably closer to 10 to the 12. And so your efficiency goes way up. And so you form a lot more stars. And so actually, most of your stars are not coming in from mergers, but coming from in situ star formation.
So you still could have merger-triggered star formation.
You still could have merger-triggered star formation. That's true.
But you argue that it's pretty small.
I couldn't argue either way at this point, actually. So.
Go ahead.
The thing that struck me most when you're reading papers that stellar mass versus stellar mass relations are consistent with no evolution over the whole integration. That's actually different from all previous other simulations. So could you comment on that?
So this plot. So yeah, so yes, we're seeing slightly less evolution. What, sorry, what's that?
I think you're seeing greatly less evolution. Right?
Greatly less evolution.
No evolution at all, where I think in most places, and actually in your previous
Yeah.
papers too, it was
Yeah.
significant evolution.
Yeah. So the best answer I can give to that is actually to look at the comparison plots for stellar mass to halo mass relationship with other people at redshift 1 and redshift 3. At redshift 1, we're basically in agreement. At redshift 3, the stellar mass functions are different enough that depending on which one you use, you can get a vastly different amount of evolution. And so that is one concern with our results, and something that we're thinking about, what's the best way to get around, to understand where that kind of discrepancy is coming from. So I'd be happy to talk with you more about that.
Richard?
Yeah.
So, Peter, well, you know the mission lines, optical mission lines, about several presentations can have quite a bit of an effect on the stellar masses when it refers to these high redshift samples. How would your results change, your modeling results change if, in fact, the stellar masses for, say, the redshift 5 to 8 samples were, say, 0.2x lower than it would have worked, say, using the Gonzalez stellar mass one ratios?
Yeah, so what would happen is these stellar mass to halo mass ratios would come down by that amount. But actually, I mean, I should mention that we include the possibility that the observer's stellar masses are wrong. And so actually in our best fit model, we don't find that everything is perfectly consistent at the very highest redshifts, but we actually allow for an offset of about 0.2 dex in terms of the observational stellar masses being higher than the true stellar masses. And so actually, I don't think this would affect our results a huge deal if the very highest redshift stellar masses came down. Yeah.
We're a bit over time here, and there will be some time for discussion after this last talk. So let's hold off on those, and we'll move on to the next speaker.